Let me pick from where we left in the last video. So we were discussing the basics of PN junction diode, and I derived these two relationships. So they relate the depletion width on the P side and the depletion width on the N side, and these are the two variables, and these are the two equations. So this is equation number 1 and equation number 2, and I can solve for these two equations, and I can express these depletion widths on the N and P side regions, and I can express them in terms of these known numbers, such as the doping concentration of acceptors on the P sides and the doping concentration of donors on the N side, and this other term, which is the built-in voltage, which I'll talk more about in this video. So I get these two relationships, and I get this relationships for xn and xp, and then I can further essentially express my overall the total depletion width, which is the sum of the depletion width on the N side and the sum of the depletion width on the P side, and I get this formula for my depletion width, where it's related to the doping in this form. So one thing which I can immediately recognize is that my depletion width is essentially inversely related to the doping I have on that region. And let me illustrate that by using this equation. So this says that the overall charge neutrality is has to be maintained. So the depletion width multiplied by the doping density has to be equal on both the P and N side. So now let me consider this case. So this let's say this junction was PN junction with equal doping of P and N types, but I'll consider an asymmetrically doped PN junction. So I'll essentially denote this by P plus, meaning a much higher doping on the P side, and then this is going to form a junction with this N-type semiconductor, which has a much lower doping concentration as compared to this P-type. So what I see over here is that my ND, which is related to the doping of the N region, is much smaller as compared to NA. So I have this relationship over here. So what I have over here is NA is much larger as compared to ND. And what that would result in is that xn would be much larger as compared to xp, because the multiple of these two has to be the same. So what is indicating is that if I have this p plus n junction, most of my depletion width would essentially lie in the N region, because my depletion width in the N region is going to be much larger as compared to the depletion width in the P region. So I get this relationship where my xn is going to be much larger than xp. And I can observe that using this individual equations for the depletion width in the N and P region as well. So what I've stated is that NA is much larger than ND. So the division, or this division of the two, or the NA by ND, has to be much larger than 1. And I see NA by ND occurring over here. So my XN is going to be very large. At the same time, I have this term in reverse over here. So I have ND by NA, which is going to be very small. So XP is going to be very small. So what a good statement to always keep at the back of your mind is that depletion, most of the depletion width always lies in the lightly doped region. So if you have an asymmetric junction, most of your depletion region is going to be occurring in the lightly doped region, which happen to be N-type region in this case. And this is something which is used very often in all the devices which make use of PN diodes. So the only other term which is I need to investigate a little more is what is this VBI, and how is it related to the doping in the PNN regions. So let me make use of some band diagrams over here. So I'll draw essentially a p-type semiconductor, and in my p-type semiconductor, my Fermi level is close to the valence band, and then I have this n-type semiconductor in which my Fermi level is close to the conduction band. So this is my p-type semiconductor, and this is my n-type semiconductor. Also, I know that for reference, I'll draw the intrinsic energy level, which approximately lies in the middle of your band gap. So this is my conduction band. Let me write in the same color. So this is my conduction band, this is my valence band. Similarly over here, this is my conduction band, this is my valence band, this is my Fermi level, this dotted blue line, and then this dotted yellow line is my intrinsic energy level. So when I'm in equilibrium, I can essentially have no current flowing, so I can connect the Fermi level between my P and N region. So this would be connected, and then I can invert my potential profile, and then I can connect the P and N regions using this continuity in the band. So it's just the inverse shape of my potential profile, and that would be the same shape of this intrinsic energy level as well. So now the concentration in my PNN semiconductor are related to the how far is this Fermi level from my intrinsic energy level. So I know that for an N-type semiconductor, the number of holes is essentially related to this difference in the position of the Fermi level. Let me call it phi Fn, and it's related to essentially difference between EF and EI by this relationship, where it varies exponentially depending upon how far is my Fermi level from my intrinsic energy level. So I know this relationship, and then I also know that for my p-type semiconductors, I'll call this phi p, the number of holes is essentially related to again the intrinsic carrier concentration, and it depends upon how below is my Fermi level from my intrinsic energy level. So it's related by again this relationship. And these potentials, my built-in potential in my PN junction is essentially the total potential difference between this PNN region. So this is my built-in potential, and I can take that reference, instead of taking that with reference referencing that to the conduction band, I can reference that same built-in potential to this Fermi level, and I see that this built-in potential is equal to this this phi p, that is the difference between the Fermi level and the intrinsic energy level on the p side, plus this phi n, which is equal to the difference in the Fermi level and the intrinsic energy level on the n side. And these are related to the carrier concentration using these two formula. And I also know that my carrier concentration on the N-type region is equal to Nd. So this would be equal to Nd. And similarly, this concentration of holes on my P-type region, this would be equal to Na. So then I can take a log of these two equations, and that basically gives me an expression for this phi n and phi p. So this phi n, actually let me correct this mistake, this is phi n. So this phi n on the n-type semiconductor, it depends upon the doping density in the n-type semiconductor. Similarly, this phi p, it depends upon the concentration of acceptors in the p-type semiconductor. And this built-in voltage is basically it's equal to the sum of this phi p and phi n, and that depends upon the product of the doping density on the n side with the product of doping density on the p side, and it's given by this formula.